Okay, so at this point you are familiar with conversion factors, ratios that we can use to convert between different types of units. And what we're going to do now is start applying that to some actual chemicals. How can we convert between units of one chemical to different units of the same chemical, and eventually we're going to learn how to convert between units of one chemical to units of another chemical in a process called stoichiometry. So to start us out, how these problems work is you always start by identifying your known. What is the number you are given or the quantity you are given in the problem, and of what substance, and what unit are you trying to convert that substance to? So in this problem here, we're told to determine the mass of 0.85 moles of potassium nitrate. So to start us out, we have to figure out our known. In this problem, we're told we have 0.85 moles of potassium nitrate, 0.85 moles of potassium nitrate. So what are we trying to figure out in this question? We are trying to take this number and convert it to a quantity of mass, and units of mass are in grams. So we're trying to get 0.85 moles to grams of potassium nitrate. We're working with the same substance here, so all we need to be able to do is figure out what's the ratio that takes us between moles and grams. So on Monday, you learned that if you're trying to go from moles to mass or mass to moles, you need a molar mass conversion factor. So there's another resource that I've created for you called the mole map. Let me talk you through how this works. So if you are lost in the deep, dark abyss of navigating a stoichiometry problem, you can orient yourself using the mole map. So the way that it works is each of the colored squares represents a known unit, and then each of the arrows represents a conversion factor. The number of arrows you cross through to get from one unit to another are the numbers of conversion factors that you need, and each of the conversion factors is labeled with the name of the conversion factor that they represent. So for this one, we started with some known quantity of moles, and we're trying to get to mass. So if we take a look at our mole map, we're starting out with a known quantity of moles of substance A. At the end of this problem, we're trying to figure out the number in mass, the number of grams of that same substance. So I'm sticking with substance A, meaning I'm on the left-hand side of this map here. And to get to mass of A, I go through this arrow right here, and that's going to land me in units of mass. So to get from moles to mass, I go through one arrow, which means I need one conversion factor in my problem. And that conversion factor is the molar mass conversion factor. Molar mass is always going to be grams per 1 mole of that substance, however many grams per 1 mole. So if I go back down to my potassium nitrate, I start out stoichiometry problems by writing your known as a fraction over 1. So 0.85 moles of potassium nitrate over 1. This is our known quantity. So from the mole map, we saw that we are going to take our known quantity and we are going to multiply it by the molar mass conversion factor, which we saw was some number of grams per 1 mole of that substance. So for potassium nitrate, we have to decide, do I want to plug this in as moles over grams or grams over moles? Since it's a conversion factor, it means it's equal to 1, so both of these things would mean the same quantity. It just depends on how you want to orient your units. So you need your units to always be canceling out. So the units of your numerator in your first factor must be the units of the denominator in your second factor, so that way they can cross cancel. So for this one, I will be using this conversion factor right here. So in every 1 mole of potassium nitrate, there are some number of grams of potassium nitrate. So to calculate molar mass, you would have to be able to take the masses from the periodic table. You multiply them by the number of atoms you have in your compound and add them up, and that's going to get you your molar mass. So for potassium, it's 39.0983 grams per mole. This is depending on the periodic table you're using. Nitrogen, 14.07 grams per mole, and oxygen's 15.999. In the formula, we have 3 oxygens, so we got to multiply that number by 3. When we add all of this up together at the end, we're going to get a molar mass of 101.104 grams per mole. So this value right here is our mass per 1 mole of potassium nitrate. So I can plug that into my formula right here, 101.104 grams of potassium nitrate per 1 mole of potassium nitrate. So this will take us to the end of our dimensional analysis setup. All we have to do is plug it into our calculator now. Our moles cancels with our moles. When we throw this in our calculator, you're going to get some number that looks like 85.9384, blah, blah, blah. But we want to round this off to a certain number of significant figures. So in our problem, we have 2 significant figures in the number we're given. So we're going to round off our answer to 2 significant figures. So to do that, we take our first 2 digits and we're going to use the third to round our number. So at the end, our actual answer will be 86 grams of potassium nitrate. Can't forget those units. So if we go down to look at the next problem, this one's going to ask us how many molecules are in 0.233 moles of water. So let's start out by determining our question. Our known quantity here is 0.233 moles of water, and we are trying to convert this value to molecules of water. I recommend writing out your question setup this way because it always gives you your starting and your ending units, which really helps you when you're using the mole map, but it also helps you check at the very end, did all of your units cancel to get what you wanted out. So we're starting with moles of a substance and ending in molecules of that same substance. So if I go back up to our mole map here, we're starting in moles, which means we're going to start at this purple square right here. And at the end of our problem, we want to end up in molecules. So we want to end up in this box here. Remember that particles is a umbrella term, so we can label anything as a particle, but it can get more specific. Atoms, molecules, electrons, formula units, whatever. So for us, we're trying to get to molecules, which is particles. So to get from moles to particles, I have to cross through this arrow right here. So I need 1 conversion factor, and that conversion factor is going to be Avogadro's number. So Avogadro's number of particles per 1 mole. Go back down to my setup here. So we're going to start out with our known. We're going to multiply that by Avogadro's number, conversion factor. So start by plugging in your known, 0.233 moles of H2O over 1. There's our starting fraction. And we're going to multiply this by the conversion factor. So here we got particles per 1 mole or 1 mole per Avogadro's number of particles. Take a second to think about which one's going to make your units cancel. And hopefully you chose this one right here. So we're going to plug in 1 mole of water on the bottom. And on the top goes Avogadro's number, 6.02 times 10 to the 23rd molecules of H2O. So now this unit will cancel with this unit because they can cross cancel. And at the end, we're left with molecules of H2O, which is exactly what we wanted. So if you pause and throw this answer in your calculator, try and round it to the correct number of sig figs, box your answer, and then come back and check with what we've got here. So hopefully when you put in your final answer to the calculator and you rounded, you ended up with 1.40 times 10 to the 23rd molecules of H2O. So remember, when you're putting in numbers in scientific notation into your calculator, you want to use that EE button. That E means times 10 to the, so it makes it a lot easier and limits the amount of errors that you will likely make when putting a bunch of stuff in all at once and limiting the amount of parentheses you need. Remember, you are smarter than the calculator. You got to tell it what to do. So if you're putting this number in your calculator, you want to make sure your calculation looks like this: 0.233 times 6.02 E23. That should be what shows up in your calculator box when you're trying to get this number out. To unlock that E button, you may have to, depending on your calculator, you may have to hit that second key and search for it. But oftentimes it shows up as an upper number, not a normal key on your calculator. Okay, let's go down and do another practice problem. How many atoms of iron are in a 5-gram sample of iron? So let's write out our question here real quick. What's our known number? 5.6. Now my pen doesn't want to work. 5.6 grams of iron. And I'm trying to convert this to a known quantity of atoms of iron. Okay, so if we go back up and look at our mole map, let's see where this one's going to take us. Grams to atoms. Okay, so starting out with grams, which means I'm starting in this mass box right here. Now I want to get all the way to atoms. So if I do that, I have to travel down this arrow here. That's going to take me to the moles box. Now where do I want to go from here? Well, I want to go to atoms, and I'm still working in the same substance, so I need to stay on the left side of the mole map. So I need to go down this arrow, and that's going to take me to atoms of the same substance. So this is where I want to end. This time, I've gone through 2 conversion factors. So if I'm going through 2 conversion factors, that means I need 2 ratios in my setup in order to get out the units that I want. My first arrow that I went through is the molar mass arrow, which means my first conversion factor needs to be molar mass. My second arrow I went through is Avogadro's number, so my second conversion factor is Avogadro's number. If I go back down here to set this thing up, I start out with my known. I'm going to multiply it by the molar mass conversion factor, and then I'm going to do another conversion factor that's going to be Avogadro's number. So to set this thing up, I start with 5.6 grams of iron. I need to multiply this by the molar mass conversion factor. Grams per mole or moles per gram? Think about which one's going to allow your units to cancel out. It's got to be grams, so that means that grams of Fe has to go in the denominator here. Luckily, this is just an element for us, so its molar mass we can pull directly from the periodic table to be 55.847. And on the top, 1 mole of iron. Remember, molar mass is always the grams per 1 mole. Same thing with Avogadro's number. It is always Avogadro's number per 1 mole. So how am I going to set up this conversion factor to get my units to cancel? Moles has to go in the denominator. So I'm going to get 1 mole of Fe down here. And in the numerator, I got to have Avogadro's number, 6.02 times 10 to the 23rd atoms of Fe. Now when I throw this in my calculator, everything should cancel. Grams cancels with grams, moles cancels with moles. And in your calculator, you should have 5.6 times 6.02 times 10 to the 23rd. Hit the enter key. Then divide 55.847. If you do it in steps like that, it's going to be a lot less likely that you'll make a mistake. So when you get your final answer and you round it to the correct number of sig figs, you should end up with 6.0 times 10 to the 22nd atoms of Fe. All right, so these have all been conversions between the same substance, but this is not where the true power of stoichiometry lies. Stoichiometry really is used to figure out how much stuff you can get if you have a chemical reaction. So from any substance participating in that chemical reaction, you can know the quantity of grams, moles, or atoms and get to any of the other quantities, grams, moles, or atoms of any substance participating in the chemical reaction. You just have to make sure that your equation is starting out balanced. So if I give you this general reaction here, let's say you have element A reacting with element B. These two things are going to come together to form compound AB3. then I've balanced the reaction for you at 2, 3, 2. So for this reaction, what this is telling us is that we need 2 moles of substance A to react with 3 moles of substance B2 to give us out our product of 2 moles of AB3 at the end of this reaction. The coefficients in front of each substance in the balanced chemical reaction equation they tell us how many moles. They tell us how many moles we need of everything here. So these values we can use as mole ratios to help us convert between different substances, different values of different substances in this chemical reaction equation. And again, your mole to mole ratio has to be from the balanced equation. Always start from the balanced equation. So let's consider the combustion of methane. This is a combustion reaction, so our product should always be the same at the end. What should those products be? Carbon dioxide and water. Take a second to look at that reaction. Does that seem balanced to you? Hopefully you said, no, it's not balanced. We have to balance it. And you're exactly right. So to balance it, we put a 2 in front of our oxygen there and a 2 in front of our water. Now we're good to go. Now we can start using conversion factors. We can start using mole ratios now that we have the balanced reaction. So if we're going to try and figure out how many moles of oxygen are needed to react with 0.4 moles of methane in this reaction, we have to think about our mole ratios in the reaction. This reaction tells us in order to make this work, we need 1 mole of methane to react with 2 moles of oxygen. When this happens, we're going to get out 1 mole of carbon dioxide and 2 moles of water. So for this reaction, we can start by setting up our known quantity. We have 0.400 moles of methane. And I need to figure out how many moles of oxygen I need to react with. So to do this, I need a mole to mole ratio. Let me go back up and show you this on the mole map. So what we've essentially done is we've started unlocking the left and right hand sides of the mole map. We can now go between them, and we can do that using mole to mole ratios. If you are trying to convert between grams or particles of one substance and 2 grams or particles of another substance, you cannot do this without going through the mole to mole conversion factor. So for us, we're starting with moles of one substance and we're trying to get to moles of another. So I only have to go through the one conversion factor, and that conversion factor is the mole to mole ratio, which I get from the balanced chemical equation. So the mole to mole ratio just tells us how many moles of one substance do we need per moles of the other. Well, for this one, for every 1 mole of methane, we find from this number here, we need 2 moles of oxygen. Why did I set up my conversion this way? Why did I put 2 moles of oxygen in the numerator? That's because I need my units to cancel. So by setting it up so that moles of methane are in the denominator, I can get them to cross cancel with the moles of methane in the numerator from my first known ratio, my first known fraction. So here I can cross cancel these things. 2 times 4 is 8, which means 2 times 0.4 is 0.8. So our final answer is 0.800 moles of oxygen. So if we were running this reaction, we would need 0.8 moles of oxygen to react with our 0.4 moles of methane. So we can use mole ratios to help us to convert between values of different substances. So now if we're going to try and take 0.25 moles of oxygen, we want to figure out how much CO2 we can produce. Let's assume here that we have unlimited amounts of methane to react. So for our question, our setup here, we're starting out with 0.250 moles of O2, and I want to convert this to the mass of CO2 that I could produce. So let's go back up and look at our mole map. Here, I'm starting out with moles of oxygen. So I'm starting in this box. Now I need to get to mass of a different substance. So I have to first convert to my different substance using the mole to mole ratio. Then I can climb this arrow to get up to mass of that different substance. So my first conversion factor that I need is the mole to mole ratio. The second conversion factor that I need is the molar mass. So let's write that in our formula here. We're going to start with our known. We're going to start with our known right here. We are going to multiply that by the mole to mole conversion factor, and then I'm going to multiply that by the molar mass conversion factor. So our known here is 0.250 moles of O2. The mole to mole conversion factor tells us how many moles of each substance we need. So looking at the balanced chemical equation, I have 2 moles of oxygen per every 1 mole of CO2. Okay, so now at this point, my moles of oxygen have now canceled out. That's my first conversion factor. The second conversion factor I need is the molar mass conversion factor. So this is going to take me from moles of carbon dioxide to grams of carbon dioxide. So in 1 mole of carbon dioxide, remember that has to go in the denominator because I need my units to cancel, there's going to be some number of grams of carbon dioxide. So you'd have to pause, calculate the molar mass of carbon dioxide. It is 44.008 grams. So now at this point, my moles cancel with my moles. You plug this in your calculator, round to the correct number of sig figs, and hopefully when you did that, you got 5.50 grams of carbon dioxide. All right, last problem on here we're going to practice doing. If we have 35.65 grams of methane, how many grams of carbon dioxide will be produced? Again, this time assuming we have unlimited O2. So to start us off by writing our question, we have 35.65 grams of methane. We're trying to convert that to grams of CO2. So this time on our mole map, we are starting out with mass of one substance. So we're starting here with mass of a substance. I need to end up in mass of a different substance. Ooh, all the way over here. Wow. Okay, how many arrows do I need to go through to get there? 1, 2, 3. A 3-step conversion factor in which I use the same conversion factor twice, but I'm using it for different substances. So the conversion factor will not be the same, or the ratio will not be the same. Okay, so let's go back down here. We are now going to take our known. We're going to multiply that by the molar mass conversion factor. Then we're going to multiply that by the mole to mole ratio. Then we're going to multiply that by the molar mass conversion factor one more time for the other substance. So take a second to pause this video, try setting it up on your own, and then come back to see if your setup is correct. Once you've finished, hopefully this is what you end up with. All right, rounded to the correct number of sig figs, you should end up with 97.80 grams. Your numbers may be a little off depending on if you use different molar masses, because from different periodic tables, you're going to get a different mass represented on there. But this is what you should end up with.